All right, guys, hello again and welcome to G Squared Academy, where excellence is epitomized. Right? So, in today's video, what we're going to be looking at is the Born Haber cycle. Okay, so Born Haber cycle comes under thermodynamics or thermochemistry, energetics, whatever you want to call it, really. And the Born Haber cycle, to put it simple, is just Hess's law applied to the formation of ionic compounds. That's what it is. So you are applying Hess's law, which you would have seen before, law to the formation of ionic compounds, right? Which I'll put as CPDS. Now, ionic compounds, the most popular ionic compound that most people would know is sodium chloride. So there is a direct route, and if you remember Hess's law says that there are multiple routes to get to a certain point, right? And it doesn't matter which route you take. As long as your beginning and your ending conditions are the same, then the energy transformation within that process will be the same. So it doesn't matter which route you take. Fundamentally, that's what we're looking at. It doesn't matter which route you take as long as your starting and your ending conditions are the same. So that's Hess's law, right? So now the Born Haber cycle, as I mentioned, is looking at ionic compounds, okay, and the formation of these ionic compounds under standard conditions, of course, but using an indirect method. So clearly, there must be a direct method of forming the ionic compound. So what we're going to look at now is the direct method of forming the ionic compound. Okay, so we directly can make sodium chloride, right? This is the direct method of forming sodium chloride. Okay, so we're going to make sodium chloride from sodium ions and sodium solid and chlorine gas under standard conditions, of course. So sodium is a solid, chlorine is a gas, and since you're trying to make 1 mole of this substance over here, then of course you have to make this half of a mole. This is Cl2, so you have to make it half of a mole because this has to be 1 mole. So to balance the chlorine, you have to make it a half. Okay, so now the indirect route for making sodium chloride would be to make it from the gaseous ions. So you're making it from the gaseous ions. So we can make sodium chloride directly from sodium and chlorine, right? Gas, or we can make it from sodium ion and the chloride ion. So this is an indirect route. The Born Haber cycle simply looks at how you change sodium solid to sodium gaseous ion and chlorine molecule to the chloride ion in the gaseous form. So that's all the Born Haber cycle does. And so now we can call this, and let me change the color of this marker here now. This is the enthalpy of formation, standard conditions. And since this arrow is pointing this direction, we can call this the enthalpy of lattice formation, since it's going that direction. Invariably, we could actually draw the arrow in that direction, and that would be lattice dissociation enthalpy. All right, but we're drawing it this way. So what we do now is we're going to convert sodium and chlorine to these two species, right? And that's our Born Haber cycle. So first of all, let us look at the sodium. You can choose anyone. You can do both of them at the same time, but I prefer to do one at a time for simplicity. Okay. So here we go. We're going to do the sodium first. The first thing we want to do to the sodium is convert it to a gas. So we're going to have Na gas, right? Plus a half mole of chlorine gas. Yes, so what we did there, as you can see, all we did was simply convert the sodium solid to sodium gas. Now, if you remember the basic chemistry that you learned when you were looking at matter, you'd recognize that this is actually sublimation from a solid directly to a gas is sublimation. Okay, but in the context of energetics, we would define it as atomization. So this step here, and I'll change the color, is delta H. This is a delta H, theta, atomization. And you can write sodium there so that you're not confused. Okay, so now we have sodium as a gas, but we need it as an ion. Okay, so now we're going to change the sodium to an ion. So we go up again. Now, one thing I failed to mention earlier was that you'll notice that arrows go downwards and some go upwards. Arrows which point upwards, like these ones, these indicate an endothermic process, which means that you have to absorb energy to get to those, for those changes to occur. And invariably, these ones which point downward are exothermic processes which release energy for those changes to occur. I'm just shortening this arrow here because I may run out of space. All right, so let's go now. So we are now going to convert our sodium gas into an ion. So now that's Na plus, right? Plus 1 electron because it's giving up an electron plus a half mole of chlorine gas. Okay, there you go. So that now is your sodium being a gas. It's a gas and it's an ion. So we have that for sodium now. What we need to do now is do the same thing for chlorine. Okay. All right. So now we have our sodium as a gas. You can see that there, sodium ions as a gas. We have 1 mole of electron and half a mole of chlorine gas. But remember, what we want is this over here. We want chloride ions in the gaseous form. Okay. So now this process here was actually the delta H theta of ionization. I should change ionization energy, IE. Let me change the color for that one. All right. So that one is ionization energy. Okay. IE. So that's what we did there. Now let us change the chlorine now. So we're changing the chlorine, right? And we still have our sodium. We still have our 1 mole of electron, putting back the state symbols, right? But now we have that chlorine atom. So this is atomization of chlorine here because this is a chlorine molecule. Cl2 is chlorine molecule. And all we're doing it, and basically we have half mole of chlorine molecule. All we're doing is just splitting that bond. So that Cl bond, which I'm going to write right here, Cl bond, we're splitting that Cl bond to give just chlorine atom. So that's what we did there. So this is kind of this is the atomization of chlorine. And some people may look at it as the bond dissociation of chlorine as well. Okay, pretty much the same thing. So we're going to put this as, and let me change the color. Actually, let me change it to a different color. The delta H theta atomization. And this is for chlorine now. All right. So now that we have done that, we need to now add now the chlorine into this form. The chlorine needs to now become ionic, which means that it needs to gain an electron. Okay. So we're going to do that now. All right. So it turns out that the electron affinity, which is the opposite of ionization energy, which is what we're going to be doing now, the electron affinity of chlorine is actually exothermic. So what I'm going to do is to get over there, I'm just going to draw the arrow up and then pull it down like that. Okay, so that's just to show that it's going down. Okay, because exothermic processes point downwards in the Born Haber cycle, endothermic processes point upwards. Okay, so that is our conversion, and this of course is our delta H theta EA, and that of course is for chlorine, right? All right, so now we have completed our Born Haber cycle. So let's just do a quick recap. Okay, so we're doing a quick recap here. So basically, the Born Haber cycle is Hess's law applied to the formation of ionic compounds. In this case, we're trying to make sodium chloride over here. Now, there is a direct route to making sodium chloride, and there's an indirect route. Directly, we could have reacted sodium solid with chlorine gas to give sodium chloride. So this is the formation enthalpy, since 1 mole of sodium chloride is made from its elements under standard conditions. Indirectly, we could react sodium ion in the gaseous state with chloride ions in the gaseous state to form sodium chloride. The Born Haber cycle pretty much shows how the direct reactants are converted to the indirect reactants. So first of all, in this example, what we have done is converted sodium solid to sodium gas, which we call atomization. Then we converted the gas into ions, which is called ionization. Then we converted the chlorine molecule to chlorine atoms, and then which we call atomization, or some people may look at it as bond dissociation, and then we converted the chlorine gas into chloride ions in the gaseous state. Then we can combine these things now to form our sodium chloride. Okay, now what your examiner may ask you is to calculate the lattice enthalpy, or you can be asked to calculate anything here really, but you would be given information about everything except one process invariably. So the enthalpy of formation would be the atomization plus ionization plus atomization plus electron affinity plus lattice formation enthalpy. There you go. And if they ask you to find lattice formation enthalpy, you just need to rearrange the equation. All right. So I hope you guys find this to be quite helpful, and you may use it in your exam. All the best. This is G Squared Academy, and I'm Gilly Gills. I'll see you guys next time.